Hi guys, welcome back. I hope you've been having a good week. Thank you so much to everybody who watched the pilot of AstroBites last week. I hope you enjoyed that, and thank you for any comments that you left. I can tell you it's been pretty freaky watching myself back on the edits, but I guess that's something I'm going to have to get used to. So this is my first proper episode of AstroBites, which is pretty cool in itself. And thankfully, in terms of the astronomy news, the past week and a bit have been pretty awesome. I started trying to make these videos back at the start of the year, and unfortunately, I missed the boat on some pretty cool stuff happening, and in particular, the New Horizons probe, which you may have seen on the news right at the start of the year, which flew by and took some pretty amazing pictures of this tiny bit of rock called Ultima Thule, way out towards the edge of the solar system. And I missed the boat on that one, which kind of bummed me out. But I just shouldn't have worried. Amazing stuff is happening in astronomy all the time, and that's what I want to tell you about today. So, my first story is about the expansion of the universe and how we may be witnessing signs that there's some new physics creeping into the story of the universe's evolution we just didn't know about before. Um, so, you may already be aware that the universe is expanding, and we've known about this for quite a long time, certainly since 1929, when Edwin Hubble, the astronomer Edwin Hubble, discovered that no matter where you looked in the night sky, galaxies were moving away from us. And there was a consistent relationship between the distance of galaxies from the Earth and how fast those galaxies are moving away from us. And if you think about it, if you're here on Earth and you look everywhere in the night sky and stuff wherever you look is like flying away from you, well, that implies that the universe is expanding. And the relationship that Hubble discovered about distance and speed of expansion also tells us something actually about how the expansion of the universe has changed through time. And the idea that the universe was expanding was one that had been predicted theoretically previously, or in the years leading up to Hubble's discovery. But nevertheless, Hubble's observations were a confirmation of that idea and a real landmark in the history of physics and astronomy, and helped give birth to the modern field of cosmology, which is, of course, the study of the origin and the evolution of the universe. And in some ways preceded, of course, the formulation of the Big Bang hypothesis itself. Now, the thing is that the kinds of observations that Hubble was making back then, and they have been repeated since, require astronomers to know the distance of galaxies from the Earth very, very precisely. And that's a really tricky thing to work out. I mean, you can't just get in a car and travel to another galaxy and then report back how far you've gone. So, how do astronomers calculate distances in the universe? Well, they do so by using a special classes of objects known as standard candles. And the important thing about standard candles is that we understand how intrinsically bright they are. So if we see a standard candle somewhere in the universe, somewhere in the night sky, and we measure how bright it appears in the night sky, we can compare that to how intrinsically bright we know it to be, and that actually allows us to calculate how far away it is. Um, and standard candles are used in a whole range of different measurements of distances in astronomy. And there are two types of standard candle that are particularly important. The first are called the Type 1a supernovae. And these are exploding stars that always have the same peak brightness when they explode. So they explode, they reach a maximum brightness, and then they fade away. But that peak is always the same. And now they're pretty rare in the local universe, but they are incredibly bright and incredibly powerful. So they're really good for measuring big distances in the universe between, large spaces between galaxies and distances between galaxy clusters and that kind of thing. The other standard candles that I want to mention to you are Cepheid variable stars, which are a family of stars which pulsate. So they actually change their physical size. The envelopes of these stars actually expand and then contract, and as they do so, the star brightens and dims. But it turns out that the period over which that pulsation takes place, so the period during which the star pulses and the star brightens and then dims, and then brightens and then dims, is actually related to the intrinsic brightness of the star itself. So if you find a C-feed in the sky and you measure how long it takes for it to brighten and dim, then you can actually work out what its intrinsic brightness is. And that means that you can use it as a standard candle. Now, C-feeds are really common in the local universe, but they're much, much dimmer. So they tend to be used to measure distances within our own galaxy, within the Milky Way, or to nearby galaxies. Now, the important thing to know is that our knowledge of the intrinsic brightness of type 1a supernovae, which, as I say, measure big distances in space, is based or is dependent upon our knowledge of the brightness of C-feed variables. And here's where the news comes in, because the Hubble Space Telescope has now released a new set of observations of a large number of C-feed variables, which have tweaked the brightness of type 1a supernovae. So they've adjusted the actual brightness of type 1a supernovae. And what that means is that astronomers have had to recalculate distances to galaxies in the universe. And as a result of that, they've also had to recalculate the rate of expansion of the universe. And guess what? Well, when we compare that rate of expansion to what we expect, based upon observations of the early universe, and then factoring in all the physics we know to kind of work out what the expansion rate should be, then it turns out that the universe actually appears to be expanding at the moment faster than it ought to be. And that's really exciting because it suggests that as we try and extrapolate forward from the early universe and put in all the physics and get to the expansion rate that we expect that we should have in the universe, something's going wrong, something's missing. It suggests that there is actually some new physics at play. Now, there have been suggestions of this over the past couple of years, but there was always a chance that there was some kind of error and that was kind of skewing the results. But the new observations from Hubble reduced the likelihood of that being the case to about 1 in 10,000. So it seems increasingly likely that there's something funny going on, there's something new in the physics that govern the actual expansion rate of the universe that we don't yet understand. What could that be? Well, it's way too early to know yet. There have been suggestions that a component of the universe known as dark energy may be responsible, but that's just speculation at the moment. So a real mystery here, and who knows where it'll go, but it'll definitely generate a whole load of new research, and one that I think is really worth keeping an eye on. So I'll do just that. I'll try and keep an eye on it and keep you up to date with what's going on. Sticking with the Hubble Space Telescope, if you watched the pilot for AstroBites, I finished up that with the 29th birthday picture for the Hubble Space Telescope, which was of the Southern Crab Nebula. And this week we're reporting another amazing image that celebrates the incredible legacy of Hubble, as well as providing scientists with an unprecedented set of information about galaxy formation. And that is the first in a series of images that are due to be released called the Hubble Legacy Fields. And it should be coming up in front of you now. There it is. It's actually a composite of about 7,500 images of a region of sky about the size of the moon. And all those images have been taken by Hubble over the course of about 16 years. And the combined image includes a number of what we call deep field sites. So one, for example, is the Hubble Ultra Deep Field, which was an extraordinary image released back in 2006, in which Hubble spent a total of about 11 days just staring at a single piece of sky that seemed to be completely empty. And when it did so, the picture that it got out was incredible, because what looked like just a completely blank piece of sky was actually completely like swarming with tens of thousands of galaxies, stretching right back to the early stages of our universe's existence. So within the legacy field, there are a number of these deep field kind of observations, of which the Hubble Ultra Deep Field is one. But the legacy field itself is in general not as shallow, so it varies in kind of depth across the entire field. But it does cover a much larger area of the sky, of course, and so it contains a heck of a lot more galaxies than the Hubble Ultra Deep Field or any of the other deep field images. There are actually about 265,000 galaxies in this image in total, and that includes ones that are close to us as well as ones that are actually far away. And that's why, from a research perspective, this image is so important. Because when we look at objects at different distances in our universe, we're actually looking back in time. So, this huge canvas of galaxies at different distances from Earth is like an enormous sample of the history of galaxy formation in the universe. And if we want to understand that history, then data fields like the legacy field give us an incredible set of observations in order to do so. But for me, the other reason that this image is so important is the kind of inspiration that it engenders. I mean, I could look at it for hours. I mean, there are all sorts of stuff in it, from fully formed galaxies to tiny dwarf galaxies to like odd-shaped, kind of ripped-up galaxies. They look as though they've been kind of torn apart in collision with other galaxies. It's all there, and it's all tracking the way in which galaxies have formed since the start of our universe. And that's really cool. That's incredible. And for me, science is nothing without wonder. And that can be quite easy to forget. So for me, there's real value in these kind of images, which remind us of just how inspiring the universe really is. Also in the pilot, we talked about gravitational wave astronomy, and this is a new and exciting field in astronomy based around detecting waves in both space and time that are generated as a result of really intense gravitational fields that are changing in a very dynamic kind of way. Um, and one of the sort of primary sources of gravitational waves that we've been searching for, astronomers have been searching for many years, is the gravitational waves that are produced when you have very, very compact, very dense objects orbiting one another or colliding with one another. And when we're talking about dense objects, what we're generally talking about here are either black holes or neutron stars. A lot of people have heard about black holes, but what are neutron stars? Well, neutron stars are the remains of really massive stars that have exploded, and in the process of exploding, their cores have collapsed, and they've got squeezed so much that all the charged particles in their atoms get converted into neutral particles instead. And what that leads to is a really huge, a massive amount of compactification of the core. I don't know if that's a real word, but let's stick with it all the same. The core collapses, and the actual core of the star essentially reaches the density of atoms themselves. And if the core is above a certain mass, then there's nothing to stop the collapse, and the core just collapses into a black hole. But if it's within a certain mass range, then once it reaches the density of like atomic density, then it is actually able to stabilize itself, as it were. And these things are what we end up calling neutron stars. But because the core of the stars collapsed so incredibly, that means we've got a really, really massive, dense core. And this stuff is so compact that literally just a teaspoon of material would weigh about 1 billion tons, which is amazing. Just like a tiny little teaspoon, 1 billion tons, just there, crazy. And literally, as I've said, black holes are the only objects in the universe which we know to be more compact and we know to be more dense. Now, as I say, some of the strongest sources of gravitational waves that astronomers have been searching for many years now were expected to come from black hole pairs orbiting one another, or from neutron star pairs orbiting one another, or indeed between black holes and neutron stars orbiting each other, and merging and colliding and all this kind of stuff. And there was a fairly long search for black holes, but the first ones were actually detected by the Laser Wave Interferometry Gravitational Wave Observatory, otherwise known as LIGO, back in 2015. And by the end of 2018, LIGO, working in collaboration with another gravitational wave telescope called Virgo in Italy, I think, had detected about 10 sets of collisions, mergers between two black holes and one collision between two neutron stars. And that's all pretty cool. And it kind of hints at this whole new kind of area of science that we haven't really kind of been able to investigate up until now because we haven't been able to detect gravitational waves. But it feels like we're now on the cusp of something, of getting quite a lot of momentum into this area of research because the observations are starting to ramp up. And in late April, the collaboration between LIGO and Virgo reported 6 new potential detections of collisions between black holes. They also collected the set for different combinations of collisions by reporting the first detection or first potential detection of a merger between a black hole and a neutron star, which they calculated took place about 1.2 billion light years from the Earth. The detections still have to be followed up further. They still need more work to confirm, so we can't be in quite 100% about them quite yet. But as I say, this is exciting stuff. Gravitational wave astronomy is starting to really build up some momentum. And what we're really doing here is looking at some of the most extreme events in the universe. And as such, they're also essential testing grounds for our understanding of the laws of gravitation. So the more data we can gather about them, or the more we can try, in some ways, to actually experience what it would be like, what it's like at this extreme end of science. I mean, just try to think what it would be like to be near or in the middle of something like this, two black holes spiraling around one another and then eventually merging. I mean, what would you experience? How would your perception of space and time be warped by these incredible gravitational forces? Um, this is something we kind of we want to be able to understand or to like get a little bit close to and have some sense of what that kind of might be like. And of course, observing events at the limit of science is exactly where we're likely to find new laws and new physics. So again, this is something that's really worth keeping an eye on. And from one kind of collision to another at a completely different scale, the last story that caught my eye this week has been about new insights into the formation of our own satellite, our moon. Now, we've known for quite a while that there's something a bit special about the Earth and Moon system. For one thing, when you look at the other planets and their moons in the solar system, our moon is unusually big in comparison to the Earth. It's only 3 times smaller than the Earth, and it's about 80 times less massive. In comparison, Jupiter's largest moon, Ganymede, which is actually also the largest moon in the solar system, is about 100 times smaller than Jupiter and about 10,000 times less massive. And if you look at the other rocky planets, the inner planets of the solar system, so you've got Mercury, Venus, and Mars, well, Mercury and Venus don't actually have any moons, and Mars has two, but they're really tiny. They're both, I think, less than 30 kilometers across. So those differences between the Earth and the Moon, and then the other planets in the solar system and their moons, starts to make you wonder really about how the moon actually formed and whether it formed in the same way as other moons in our solar system. And there's been a lot of research into this, spanning over a long period of time, which includes analysing samples of rocks that have been brought back from the moon. And the leading theory these days is that the moon actually formed early in the solar system's history, about 4.5 billion years ago, when the early Earth was hit by an object about the size of Mars. And this object has been dubbed Thea, after the mother of the Greek goddess of the moon. Now, obviously, that collision very early on would have released enormous energy, and it was thought that it would have smashed the outer layers of Thea apart as well as bits of the Earth, resulting in a whole load of material being flung into space, and then that material would kind of like cool and condense and end up forming the moon that we have today. But the theory hasn't been without its problems, and in particular, although bits of the Earth both get flung into space during the proposed kind of collision, simulations of the collision so far tended to suggest that most of the material that goes to form the moon actually came from Theia. But when scientists look at the abundance of different elements in rocks from the moon, they turn out to match pretty closely what we observe in rocks on the Earth. And that's a bit odd because the chemical composition of objects in the solar system is not the same everywhere. And it's extremely unlikely that the object that we refer to as Theia would have had the same composition as the Earth. So it looks as though there's Earth stuff in space instead of Theia stuff, kind of thing. Now, new scientists from Yale and Japan think that they may have solved the problem. So what previous models of the collision between Earth and Theia hadn't taken into account was that at that time, Earth's surface was probably mostly still molten when it collided with Theia, whereas Theia was expected to have a solid surface. And when you factored that in, what you find is that the Earth's molten surface absorbs a lot more of the energy of the collision than the solid material of Theia. And that means that the magma of Earth's surface expands during the collision, and it's primarily that molten material that gets flung into space to form the moon, not bits of Theia. So what happens to Theia? Well, the model shows that Theia gets swallowed into the early Earth's hot interior, and then as the Earth reforms and the moon condenses in orbit around us. And that kind of matches actually observations of the Earth that show that it's much denser than the other planets in the solar system. And that's explained quite neatly if it's got essentially a whole other kind of planet inside it, which it's collided with early in its history. So we may be getting closer to understanding how the Earth and Moon were made, and that's pretty cool. But again, just imagine, wherever you are right now, wherever you're sitting was once a sea of molten rock. And there's something in the sky that's been there for a while, but it's getting bigger and bigger and bigger, and it starts filling the sky until it's completely blocking out the light from the sun. And then eventually it hits, and there's this enormous explosion, this enormous lighting up of everything around you. And the land, this molten land on which you're kind of sitting, just kind of heaves, and you end up getting thrown into the sky and out in space. It sounds unbelievable, but it seems increasingly likely that that's actually what happened. So just remember that whenever it's a clear night and you look up and there's the moon, that moon was once a giant bit of the Earth, and now it's there just hanging out in space. It's quite a funny thought. Okay, so that's it for this week. Thanks for watching. Just wanted to leave you with this. It's an image of the moon, which we've just been talking about, taken by a group of telescopes called Midas during the total lunar eclipse that took place in January this year. See the little bright dot that the arrow is pointing at? Well, that is the flash from the impact of a meteorite hitting the surface of the moon. And scientists believe that a chunk of space rock that was responsible for this impact hit at a speed of about 61,000 kilometers per hour and released about the same energy as 1,500 tons of TNT explosive. Some amateur observers actually watching the eclipse at the time actually reported seeing it with the naked eye, which must have been pretty cool. So there you go. Hopefully a good way to round off an episode that's talked quite a lot actually about collisions. I hope you have a good week. Leave us your comments below, and I hope to see you again soon.